So I will introduce how to simulate various types of wheel robots in NVIDIA Isaac Sim, including differential drive robot, Ackermann steering robot, Omni wheel robot, and finally Mecanum wheel robot. First of all, I will show you the simulation of a differential driving robot using the small mobile robot platform Limo from AgileX. And let's discuss about some debugging points for potential issues that may arise. And next, I will simulate an Ackermann steering robot using the same Limo. Lastly, I'd like to demonstrate about integrating Omni wheel and Mecanum wheel robots into Isaac Sim using the Kaya provided by NVIDIA and the Summit from Robotics. By understanding this tutorial, you will be able to implement all types of wheel robots in Isaac Sim and utilize your custom robot models for your research and projects. So let's get it started. Before we dive into examples, I'd like to address one thing. That is, yeah, for all the examples used in this demo, I provide both pure Python examples and Rust examples to accommodate your different preferences and needs. In order to follow this tutorial, you must clone my Github repository, that I prepared. So first, clone my repository that is named RB build robot example. I will leave the link of this repository in my YouTube video. So in my case, this is located in here. So located in here. And let's navigate into the RB real robot example and this folder. And let's navigate into USD folder. There will be an .z file. So extract this, and the next thing you have to do is let's turn on your Nucleus Navigator and Nucleus Server like this, and drag and drop the whole USD folder in your preferred location. To be honest, the location doesn't matter, but keep the location in mind because you must change the USD path in your codes in the future. And next, let's talk about how to use my GitHub codes. And this code in here has some kind of templates. To be honest, this is made through the OMNIVERSE extension template. So you can import all my codes easily by clicking this window button, and let's dive into extensions. Let's click this hamburger button on the upper right. Click the settings. In my case, let's add one more path, local path. Let's copy and paste my codes locations into here like this, and click the enter button. If you move to the third party tabs, you can find some kind of this like icon, and you can enable all my codes extensions through clicking this enable toggle buttons. And I also recommend to checking this auto loads too for the future examples. And let's dive into the code. As I said before, all the code is referencing the local USD Nucleus servers paths. For instance, in my case, now I'm working on various projects. So in my case, now I made a separate folder named RB-Lost2, and the location is projects RB-Lost2 and with robots and something like this, blah blah blah. In your case, if you change this location, or if you want to change the location, all you have to do first is changing all these USD folders locations in my codes. So keep that in mind, the location. Yes. Let's dive into the first example. Click this Isaac examples button and you can watch the new tab that is named RB Wheel Robot example is appear, and click this first tab, remove disk drive. And click the new window will be appear, and click this load button and wait a little seconds. This is the example controlling Limo using the pure Python Isaac API. So let's learn this example and watch how the robot moves. Click this play button. Robot will move forward a little bit and backward. Next. And it'll try to rotate in place. However, let's check the robot's movements. Now it's trying to rotate in place, but some kind of sleep is occurring now. Let's check it again. Robot moves forward again and backward again. Watch carefully how the robot moves in rotation. Yeah. During the rotation, a little bit of back and forth movements disappears, of course, in here. So seems like, yeah, not good in terms of precision and accuracy. Stop it. Yeah, I promise to let you know what is the problem is. Just follow me, please. Let's toggle this robot paths into from limo base to limo diff thin model. Swap the commands in here and save this file. Don't forget to typing the Control S for saving. Let's move our Isaac sim again. Let's create new world. And let's import our limo diff drive example again. Let's check it out how the robot moves changes from previous one. Click this play button. Yeah, nothing changes from moving forward and backward. However, let's check how the robot movements changes in place rotation. Yeah. Now there's no kind of slippery and sleep during the robot's rotation. So what is the difference between these two models? To show you the difference, I will activate the collision visualization for this robot. You can activate the collision visualization through clicking this I button in the upper tab and show by type physics collider and select this button, all button. It depends on your environment, but now I'm using the RTX 3080. There's no kind of buffering issue here. And as you see in here, there's a little bit slight difference between the actual wheel collision and the Limo's wheel. So to be honest, to address the rotation slip issue, I manipulated the URDF to ensure that the vertical and horizontal ratio of the wheel be equal. And I also made the robot's wheels much more thinner, like here. The green collide and green mesh is robot's actual collider property. Specifically, to be honest, the original limo-based URDF is here, and the ratio between the vertical and horizontal was 0.1 by 0.065. So it was there was some difference between the vertical and horizontal ratio, but I changed it and modified manually by making the vertical, horizontal ratio to be to 0.1. So eventually I made the vertical and horizontal ratio to be 1 by 1 to be equal. And also I made the wheel much more thinner by, in here, the cylinder length was previously 0.045, but I changed it into cylinder length to be 0.01, much more thinner. And lastly, in our Python codes, you can check that in here, this is kind of controller for differential drive robot is provided by OMNIVERSE Isaac. And here, the wheelbase, originally wheelbase means the distance difference between left and right wheel. So if we move to the URDF again, the left and right means y-axis. So y-axis between from the left to the right wheel was 0.13. However, it seems like kind of magic number appears in here, 0.43. Where does it appears? And about this, I would like to reference one link in here. Let's click this one. Yeah, I was able to gather some hints from the NVIDIA developer forums, and thank you so much for him, the name Longi Lian. Thank you so much. I love you. And what he says, and the solution from his post is here. According to this paper, the skid steering differential drive robot is equivalent to either just differential drive robot with longer wheel distance, means wheelbase, than actual config. And let's dive into this paper. And scroll in here. Yeah, the picture is what I want to say. This one is for WD skid steering robot, like our limo. To be honest, this paper is saying that this model is exactly the same as this one. So the wheelbase in Lear was 0.13 in our URDF, and we can consider it much more longer in our Isaac sim. By the way, in this tutorial, I just skip some details explanation of my code implementation. However, I've added some references like this for key points via commands. So I believe those references will make my course more straightforward to understand. So if you encounter some kind of issue during learning my examples and my Python codes, please leave any comments on my YouTube videos. The next one is controlling the same differential drive robot through loss2. The loss2 version used in this demo is loss2 Humble, which is compatible with the Ubuntu 22.44 version I'm using. And to activate the communication between the Isaac sim and loss2, the loss2 bridge extension must be activated. So ensure that this bridge extension is activated before running up my examples, and you can check that by clicking this window and extensions and typing the loss2 underbar bridge in here. Yeah, you must check that this toggle switch is enabled, and I also recommend to checking this auto load to be enabled. So let's run the example. Click this Isaac examples again and click this one, label diff drive underbar loss2, and click this load button again. I will control my robot using RQT robot string and from the loss2. So as you see in here, let's move it backward and forward and turn left, turn right in place. Rotation with the moving forward and backward. Yeah, it moves smoothly. Likewise, our previous Python demo. And mostly, in order to implement some kind of loss2 communication system in Isaac sim, we usually make some kind of visual scripting language that is named OmniGraph in our environment. You can check that by clicking this check create and visual scripting and action graph button. Let's click this some kind of pencil like button and loss2 diff drive. This is controlling OmniGraph. As you see here, we can see some kind of graph like pictures in here. There's some nodes and there's some thin threads between those nodes. So by making some kind of these like graphs that is named OmniGraph, you can make the loss2 implementation system on our Isaac sim. However, connecting all this kind of graph every time can be quite tedious and sucks. So therefore, in my case, let's dive into my code in here. This is my code. Yeah, as you see in here, I already implemented the OmniGraph entirely in Python codes. So what you want to do, what you have to do is just copy and pasting my codes. So feel free to use my examples. And all you have to do is changing those parameters. For instance, wheelbase and target prim and global path. Oh, to be honest, this is not the current example, and the limo diff loss2. This is, yeah, current example. Yeah, like this. Change the join names for your robot and the target print for your robot, and change those control parameters for your controllers. Well, I have one thing to say too. In this example, yeah, let's run this again. And in this example, I also implemented the Odometry OmniGraph too. So let's click the pencil button and click this lost to Odom button. Yeah, this is the OmniGraph for publishing the odometry topic in our Isaac sim to our lost to system. So if I run and play this my example, and type the lost to topic list, and you can find this odometry is still publishing from our Isaac sim lost to topic equal odometry like this. So what do I need this odometry? If you want to find the wheelbase that I said before for your robot, in our case it was 0.43. Yeah, the method to find this wheel distance, you can utilize my odometry for your finding wheelbase. For instance, let me say that I want to control my robot, and let me say that the angular velocity wanna be 0.5, and let's click this RQT topping monitor, and let's check this angular twist from actual odometry in Isaac Sim. Because the Isaac Sim know the absolute position and angular states of the robots, so this odometry is kind of ground truth for odometry. And as you see here, the input command is 0.5 and the output from the Isaac Sim is 0.48, so kind of reasonable. However, if I try to change my wheelbase parameter from my robot, let's swap to diff drive again and change the diff drive controller's wheelbase parameter into wheel value. This is wheel radius, sorry about that, and 0.13 again, and let's play this again. Yeah, the input command is 0.5 radian per second, and the output from odometry tree is actually 0.16, so there's a huge gap between actual command and actual output from Isaac Sim. So what I want to say is, by some kind of experiments from, yeah, something like this, you can find the new wheel base parameter for your new robot, your custom robot. So feel free to use my playfields and my examples. Next one is a demonstration for the Ackermann steering robot. Unlike differential drive robot, the Ackermann steering robot uses position control with a steering hinge. Something like, let me show you this. In Ackermann steering robot, we need two position damage, which means hinge joints for our robot steering. Unlike in our previous differential drive robots, it only requires 4 continuous joints for wheels. 1, 2, 3, 4 continuous wheels. However, in Ackermann steering robot models, let's run this again. Yeah, in here, it also requires 4 wheel continuous joints. However, maybe the front wheel. Let me show you. Where it is. Yeah, I found it. Sorry about that. 4 continuous joints here and there, and it also requires 2 positioner level load joints for steering hinge. Here, sorry about that. Yeah, here and here. Yeah. Hence, to address these new hinge attachments, I made a new URDF file named limo Ackermann and imported this new URDF and generated a new USD file through either utils and workflows. Here, URDF importer, I used this and made a new USD file for my Ackermann limo version. before beginning the demonstration, I have one news. That is, there's no Isaacson Python API for Ackermann steering. As you can see, here are differential controller and holonomic controller for with robots, which implemented with Python API, but here's no kind of Ackermann steering controller in this documentation. However, with Omniverse Physics Vehicle Dynamics, you can implement an Ackermann steering robot. So if you are interested in vehicle dynamics in Isaac Sim, please let me know your interest by leaving comments on my YouTube videos. If so, I will shoot an additional video on this topic. So let's go ahead and run the last 2 demo for Ackermann steering. This time I will click Isaac examples and the button Limo Ackermann lost to Ackermann and click this load button. And let's play our simulation. In order to control our Limo Ackermann, I will use the RQT topic publisher and let's follow me and I will publish some kind of messages to this Limo in the Isaac Sim. Yeah, in this demo, our robot will subscribe Ackermann messages topic in loss2 to control the Limo in Isaac Sim. The Ackermann messages consist of steering angle velocity, and speed, and finally acceleration and jerk. The steering angle is for the front hinge angle, and the speed is for the vehicle chassis speed. And again, let's pause our simulation. And again, I configured the system that integrates Isaac Sim with loss2 using OmniGraph. So let's create video scripting and click this action graph button again. And let's check how this loss2 Ackermann graph is configured. In Isaac Sim, there's a node named Ackermann steering, and yeah, here it is. Loss2 subscribe Ackermann drive nodes for receiving our control signal and then calculate some kind of actual positions and velocities for virtual robots in Isaac Sim. So let's examine the parameters in Ackermann steering first. As you can see, here are a few parameters related to actual and virtual robots. To achieve proper Ackermann steering control, the parameters like turning wheel radius for the radius of the wheel and wheelbase where it is wheelbase and track width will be required and need to be provided. For instance, the wheelbase refers to the distance between the front and the rear wheels of the chassis, while the wheel track refers to the distance between the left and right wheels of the chassis. One thing to mention in this tab is those track width and wheelbase in this tab are the actual value from your URD file, not some kind of heuristic values you must find through some kind of experiments like. So if you want to use my codes, all you need to do is just change and adjust several parameters from my Python codes. And while making this example, I wanted to make another version of this controlling loss2 version. This is because loss developers, including me, barely use this Ackermann drive stem type for publishing robot control for Ackermann steering a robot. We usually use this geometry messages / twist type. We usually prefer this type for publishing the control command to our robots. Therefore, I made another version of controlling OmniGraphs, and by adding a bit of logic to OmniGraph, this can be implemented. So that is exactly our next example. Let's dive into that. Let's reset our world and let's learn our next example. This one, Limo Ackermann loss2 twist and load one. Click this play button. Now you can control the robot not with Ackermann messages, but with geometry messages, twist type messages. So like this. Yeah, that is exactly what I wanted. And how can I did and how can I implement it that? What I've implemented is simply, hold on. Yeah, simply adding some kind of logic to OmniGraph to convert the linear and angular velocity to Ackermann message type. More in detail, I've utilized the relationship between the velocity and linear velocity and angular velocity. So feel free to copy and paste my codes. And if you want to understand about what does logic it means, I will leave a comment on my codes too. All right. And next one is finally Omni wheels and Mecanum wheels. Let's listen our word again. And click the button Kaya robot and load button too. And click button. During the example, the robot moves backward and forward and move to the light and then to the left. A little bit of sleep occurred in here. And finally, it rotates counterclockwise in place and clockwise in place. Remember this sequence and let's take a look at the code. And I will stop our simulation. Here's the code. And in fact, the velocity passed in the code word moves forward and backward and then left, right, and finally counterclockwise and clockwise. So, and moreover, even though I used the configuration provided by NVIDIA, we can notice that the robot doesn't move in our desired directions. So I will explain to you how to integrate Mecanum wheels with a new robot and new code. In addition, the OmniVerse is a special case of the Mecanum wheel. This is because if the wheel axis of the Mecanum wheels become perpendicular to the large wheel, that is exactly Omni wheels. Similarly, for implementing in Isaac Sim, setting the Mecanum wheels to 90 degrees will make it an Omni wheel controller. You can learn our next example by clicking this Robotnik Submit button. Let's click this load button. The robot that we use in this example is a Summit from Robotnik. This is a robot that uses Mecanum wheels tilted at 45 degrees. So let's learn our example. The robot moves forward, backward, and you can notice that this kind of error case occurs when robot tries to move left and right. Finally, the robot tries to turn clockwise and counterclockwise. Seems like this kind of issue in this example, and bear with me and let's learn another example through clicking this button. Robotnik Summit O3 wheel. So let's reset our environment and turn on our next example again. Click load button. Let's learn our example again. The robot moves forward, backward, and left. In respect of the robot, it'll be left side, or the it is right side in our side, and right. Finally, clockwise and counterclockwise. Yeah, that's it. So what is the difference between our previous example and this example? So let's talk about some points to be aware of when using Mecanum wheels in Isaac Sim. First thing is you need to set up the collision of the wheels correctly. So let's activate the collision of our models visualization in Omniverse again. So let's click this I button and navigate into physics, colliders, and click this all button. As you can see, right now, the Mecanum wheels of the summit have collisions that exactly match the visual mesh. However, if I change the model to our previous one by clicking this Robotics Summit demo, yeah, you can watch this kind of triangular, yeah, chaos mesh on the summit wheels. So in the original URDF file from the GitHub of Robotnik, they didn't consider those collisions of Mecanum and Omni wheels. So therefore, for this demonstration, I explore some open source projects and replace the wheels with compatible one. The model I reference is this one, O3DYN simulation model from the Fraunhofer Institute. So I'm so much thank you for sharing this awesome model, the Fraunhofer Institute. Yeah, I will leave the link on my YouTube too. So let's dive into code. In the holonomic controller constructor, I've passed various parameters including wheel orientations and positions and Mecanum wheels, and finally wheel axis for our new summit model. I will talk a few key points you need to keep in mind for making this holonomic controller. The first thing is about wheel orientation. The orientation of the wheel in this code has the coordination frame that is W and XYZ quaternion sequence. Usually we use XYZW quaternion sequence. So it has some kind of, yeah, this will be confused for you. And next thing is, let's check about the Mecanum angles. How can I configure these Mecanum angles? For this, I prepared some simple diagram. As you can check in the diagram, the angle reference for Mecanum angle is such that the right side is the plus x axis and downward is the plus y axis. Therefore, for summit, it has Mecanum angles of minus 45 and minus 135 degrees. Finally, there's a point to be aware during Mecanum wheel simulation. If you look at the physics scene in Isaac Sim, you will notice that the sim step per second is set to 30. If you increase this to 60 or more higher, and run the example again, you will see some kind of errors during the left and right movement. So let's run our code. Now the sim steps per second is set to 30. So nothing kind of error happens in this simulation. Yeah, nothing happens. It moves properly. However, if I increase this sim steps much more bigger, something like 60 or 120, 60, and if I run this code again, look carefully, and yeah, some kind of weird happens in here. Probably I think this is because using the Mecanum wheels increases the computational cost. By the way, for this reason, the simulation step has been lowered to 30 in this example. Let's check this again. Yeah, now it's all light. Everything is good. And finally, the last one is controlling our Mecanum wheel over wheel loss too. Yes, last example. Click Isaac examples, and this last one. Robotnik Summit or 3 wheel loss 2. Load 1. And let's click and play this. Since our architecture robot steering, it cannot give plus or minus y-axis velocity to our robot. Therefore, in this example, I will give the velocity to our robot through this architecture topic publisher. So linear 0.2 velocity and linear minus 0.2 velocity, and the special thing for Mecanum wheels plus 0.2 y-axis velocity most properly, and minus y-axis too. And finally, let's control our robot in state rotation for 0.3 maybe, and minus 0.3 maybe. And let's check the OmniGraph again. Edit action graph and click this one, loss to holonomic twist OmniGraph. I configured the system using the holonomic controller node. However, if you look closely at this graph, you will notice several constant nodes. Constant double here, and here again. Total 3 constants. These are gain parameters to reduce the error between control and odometry, as in the previous differential drive example. So you will need to experimentally find those values, and I will show you how to do soon. And lastly, you will notice that the navigate constant is multiplied to the angular velocity. This is for correcting the error of rotating, as you saw in our previous Kaya example. So let's run our code again. And to be honest, yeah, let's check this one. Yeah, to be honest, here's kind of issue in this example. That is, if the angular velocity becomes too high, our robot will bounce occasionally like this, bounce and bounce a little bit. I think it's because the calculation might not be completed within the simulations tab. However, yeah, to be honest, this example has some kind of issue with about that. And I will show you how to optimize your those constant values and find your proper parameters. Let's give some kind of maybe 0.5 radian per second angular velocity, or maybe 0.3. And if you want to use my code in your actual and your customized robots, check the Odometry topic and check this twist and angular velocity. What you have to do is first check the difference between the odometry angular z velocity in this case and the actual velocity you gave to your robot. In this case, it has a little bit of differences, but seems like reasonable. However, if you change these constant values into, where is angular velocity constant? This is angular velocity, so that gain parameter might be here. So minus 0.14. If I change this value into, what about 0.114? And if I run this again, you can notice that the actual value from the Isaacson becomes so much slow. So what you need to do is adjusting this parameter to make those two values match. Yeah, in this video, you learned how to integrate differential drive, Ackermann string, and Omni Mecanum robots into NVIDIA Isaacson. If there's any topic you'd like me to cover in the next video, please leave a comment below. Don't forget to subscribe and click the like button. Bye bye.